On the night of October 29th, 2025, just moments before he was set to walk into a high-stakes meeting. With Chinese President Xi Jinping in South Korea, President Donald Trump posted a message on Truth Social that immediately sent shockwaves through defense circles around the world. Because of what he called other countries' testing programs, he wrote, he had instructed the Department of Defense to begin testing American nuclear weapons again on an equal basis with everyone else, and that process would begin immediately. It was a stunning reversal of a policy that had held for 33 years. The United States had not detonated a nuclear test device since 1992, relying instead on computer simulations to maintain confidence in its arsenal. The announcement came just days after Russian President Vladimir Putin revealed that Russia had successfully tested a nuclear-powered cruise missile known as the Burevestnik, capable of flying more than 8,000 miles. And, only a day before Trump's post, a nuclear-powered underwater drone called Poseidon launched from a submarine and run, for the first time, on its own onboard nuclear reactor. Within hours, experts, lawmakers, and military analysts were scrambling to figure out exactly what Trump meant, since no country on Earth had actually detonated a nuclear test explosion since North Korea did in 2017, and neither Russia nor China had done so since the 1990s. Nobody was entirely sure whether America was about to physically detonate a warhead in the Nevada desert for the first time in a generation, or whether this was a warning shot aimed squarely at Moscow and Beijing. What that moment made painfully clear, though, was that the nuclear question, the one humanity has been trying to manage since 1945, was suddenly back at the center of global politics in a way it hadn't been in decades. And it raises a question that almost nobody stops to actually answer with real numbers. Just how powerful are these weapons, really? Are they capable of the planet-ending devastation we've all absorbed from decades of movies and pop culture, or has that reputation outgrown the reality? What would an actual nuclear war do to Earth? And is there a weapon out there, one that's never officially been built, that would be so much worse than anything currently sitting in a missile silo that even talking about it should make you uneasy? Let's get into it, because the answers are stranger, and in some ways scarier than most people realize. To really understand how we got here, it helps to go back to where this all began, because the nuclear age is younger than most people assume. The very first nuclear explosion in human history took place on July 16, 1945, in the New Mexico desert, when American scientists, working under the Manhattan Project, detonated a plutonium implosion device during what became known as the Trinity test. Less than a month later, on August 6, 1945, the United States dropped a uranium-based bomb nicknamed Little Boy on the city of Hiroshima, with a yield of roughly 15 kilotons, followed 3 days later by a plutonium bomb called Fat Man over Nagasaki, yielding around 21 kilotons. Those two bombs remain, to this day, the only nuclear weapons ever used in actual warfare. And together, they killed well over 100,000 people, with tens of thousands more dying in the months and years that followed from radiation-related illness. What's genuinely staggering, when you compare those numbers to what came later, is just how small those first bombs actually were next to what humanity would go on to build within less than 2 decades. Little Boy and Fat Man were measured in kilotons, thousands of tons of TNT equivalent. Tsar Bomba, by comparison, was measured in megatons, millions of tons, meaning the single most powerful weapon ever detonated was roughly 3,000 times more powerful than the bomb that leveled Hiroshima. That escalation from kilotons to megatons in less than 20 years is really the story of the entire Cold War arms race compressed into one comparison. Nuclear warheads remain the single most destructive category of weapon humanity has ever built, and the raw numbers involved are still staggering even after decades of arms reduction. According to the Federation of American Scientists' most recent accounting from early 2026, 9 countries around the world now possess a combined total of roughly 12,187 nuclear warheads. Russia holds the largest stockpile of any nation on Earth, with more than 5,400 warheads, while the United States follows close behind with just over 5,000. Of that global total, only around 9,145 warheads are actually sitting in active military stockpiles ready for potential use, with the rest retired and awaiting dismantlement. And of those active stockpiles, roughly 3,900 warheads are actually deployed with operational forces, mounted on missiles, or stationed at bomber bases, with somewhere between 2,100 and 2,200 of those kept on high alert, ready to launch on short notice. That's still an enormous number, more than enough to reshape the planet many times over. Beyond Russia and the United States, a handful of other nations are formally recognized as nuclear powers, including China, France, and the United Kingdom, though their arsenals are far smaller by comparison. China's stockpile has been the fastest growing of any nuclear power in recent years, though the U.S. intelligence community still estimates it at only a few hundred warheads. a fraction of what Russia or the United States maintains. Beyond those 5 officially recognized nuclear weapon states under international treaty law, 4 more countries are known or widely believed to possess nuclear arsenals of their own, even though none of them are formally recognized under the Non-Proliferation Treaty. India is estimated to hold somewhere around 180 warheads, Pakistan close behind at roughly 170. And both countries have been steadily expanding their stockpiles for years, driven in large part by the tense, decades-long rivalry between them. Israel has never officially confirmed possessing nuclear weapons at all, maintaining a long-standing policy of deliberate ambiguity, but independent estimates place its arsenal at around 90 assembled warheads, with enough fissile material on hand to potentially build closer to 200 if it ever chose to. North Korea remains the newest and most unpredictable member of the nuclear club, having withdrawn from the Non-Proliferation Treaty back in 2003, and while its exact warhead count is notoriously difficult to verify, most analysts believe it currently has enough weapons-grade material to build somewhere between 40 and 50 individual devices. The precise capabilities of any individual warhead remain closely guarded state secrets. But what is publicly known is that the most powerful weapons currently deployed carry yields in the range of 1.2 megatons, equivalent to roughly 1.2 million tons of conventional TNT explosive. Most modern intercontinental ballistic missiles are designed to carry multiple independently targetable warheads, sometimes 6 to 8 per missile, each with a yield in the range of a few hundred kilotons, allowing a single missile to strike several different targets on the way down. But, as devastating as those numbers sound, none of them come close to the single most powerful nuclear device ever built and detonated in human history, a weapon so enormous it's still talked about with a mixture of awe and disbelief more than 6 decades later. You've probably heard its name before. Tsar Bomba, sometimes called Big Ivan, detonated by the Soviet Union on October 30th, 1961, over the remote Arctic testing site of Novaya Zemlya. Tsar Bomba remains, to this day, the largest man-made explosion ever recorded on planet Earth. Modern reassessments of the test data put its actual yield at somewhere around 57 megatons, the equivalent of 57 million tons of TNT. To put that in perspective, that's roughly 3,000 times more powerful than the bomb dropped on Hiroshima. The sheer scale of the weapon made it almost comically impractical to actually deploy. The bomb itself weighed 27 tons and measured 26 feet long and nearly 7 feet in diameter, so massive that Soviet engineers had to strip the bomb bay doors and fuel tanks off a specially modified Tupolev Tu-95 bomber just to physically fit it aboard. Even more remarkably, Tsar Bomba wasn't even built to its full potential. The weapon used a 3-stage design, a fission bomb compressing a thermonuclear stage, which in turn compressed an even larger thermonuclear stage. And evidence suggests the design could have supported multiple such stages, theoretically pushing the yield past 100 megatons. Soviet engineers deliberately toned the weapon down before the test, swapping out a uranium-238 tamper, a layer of dense material that would have dramatically amplified the explosion through additional fission reactions, for a lead tamper instead. That single design choice meant fast fission was essentially eliminated, and thermonuclear fusion accounted for roughly 97% of the bomb's total yield, producing a cleaner explosion with dramatically less radioactive fallout than a full-power version would have generated. It also meant the bomber crew that dropped it had enough time to get far enough away to actually survive the blast, something that wouldn't have been guaranteed with the bomb at full strength. Even scaled down, the explosion was almost incomprehensibly large. Detonated roughly 2.5 miles above the ground, Tsar Bomba produced a mushroom cloud that climbed more than 37 miles into the sky, well past the boundary most scientists use to define the edge of space. The flash from the detonation was visible from as far as 620 miles away, and anyone caught within roughly 62 miles of ground zero without shelter would have suffered third-degree burns. Had there been any astronauts in orbit at the time, the blast would almost certainly have been visible from space. And yet, for all that power, Tsar Bomba turned out to have essentially zero practical military value. It was simply too large and too heavy to be a usable weapon, and American scientists at the time were quick to point that out publicly, which meant a bomb designed explicitly to intimidate the West largely failed to intimidate anyone at all. Interestingly, the United States actually tested its own share of enormous devices during the same era, though never anything on Tsar Bomba's scale. The largest American nuclear test, codenamed Castle Bravo, was detonated at Bikini Atoll on March 1st of 1954, and he was expected to yield around 5 megatons. Due to a miscalculation in how the weapon's lithium fuel would react, it instead produced a yield of roughly 15 megatons, nearly 3 times what scientists had predicted, showering nearby islands and a Japanese fishing boat with radioactive fallout, and becoming one of the most infamous nuclear accidents of the entire testing era. There's also a strange piece of physics at play here that most people don't realize. Testing has consistently shown that nuclear explosions don't scale up in destructive power the way you'd intuitively expect. A 100 megaton bomb releases 10 times the raw energy of a 10 megaton bomb, but because of the nonlinear way blast waves behave, it doesn't do anywhere close to 10 times the damage, more like just over twice as much. Weight, on the other hand, scales in a far more linear way, meaning a 100 megaton bomb weighs roughly 10 times as much as a 10 megaton one, making it exponentially harder to actually deliver on a missile or bomber. That mismatch between weight and destructive payoff is a big part of why nuclear arsenals moved away from ever larger single warheads and towards smaller, more numerous, more accurate ones in the decades that followed. That shift towards smaller, more precise weapons is exactly what modern missile programs reflect today, and there have been some genuinely alarming developments on that front recently. Russia's RS-28 Sarmat intercontinental ballistic missile, nicknamed Satan III by NATO as a successor to the older R-36 Satan design, is capable of carrying up to 15 independently targetable warheads, each able to glide toward and strike an entirely separate target. On the American side, the LGM-35A Sentinel is now in development as the U.S. Air Force's next-generation intercontinental ballistic missile, intended to eventually replace the aging Minuteman III, which has been in service for more than 5 decades. The Sentinel is designed to carry advanced multiple warheads as well, including variants of the W-87 thermonuclear warhead, a weapon with a yield of roughly 475 kilotons that was previously deployed on the retired Peacekeeper missile system. The fact that modern ICBMs can carry several independently targetable warheads apiece means a single missile launch today carries the destructive potential of what would have required an entire squadron of aircraft during earlier eras of the nuclear age. It's precisely this kind of ongoing modernization, on both the American and Russian sides, combined with Russia's recent Burevestnik and Poseidon tests, that helped push global tensions to where they sit today. The Bulletin of the Atomic Scientists, the organization founded in 1945 by Albert Einstein, J. Robert Oppenheimer, and other Manhattan Project scientists, maintains the doomsday clock, a symbolic measure of how close humanity sits to global catastrophe. On January 27, 2026, the Bulletin moved the doomsday clock to 85 seconds to midnight, the closest it has ever been set in the clock's nearly 80-year history, citing collapsing arms control agreements, increasingly aggressive rhetoric among major nuclear powers, and a broader failure of global leadership to address existential risks. So, what would an actual large-scale nuclear war between two major powers really look like, if it ever happened? There are simply too many variables to predict with total precision, including how many missiles on either side might be intercepted by missile defense systems before reaching their targets, but the broad shape of the scenario is grimly well understood among defense analysts. Because modern hypersonic glide vehicles are extraordinarily difficult to shoot down once they're on their way in, the assumption among most experts is that the damage on both sides would be catastrophic, almost no matter what interception capability exists. Even the most advanced missile defense systems in existence today, layered networks like the American ground-based mid-course defense system or shorter-range systems like THAAD, were designed with the assumption of intercepting a handful of missiles from a smaller nuclear state, not blunting a full-scale exchange between two major powers, each capable of launching hundreds of warheads simultaneously. The general sequence tends to follow a familiar and horrifying pattern. One side launches, the other detects the launch and responds in kind before the first wave even arrives, and submarine-based ballistic missiles from both sides join the exchange shortly after. The very first detonations, particularly any at high altitude, would generate electromagnetic pulses capable of frying electronics and collapsing power grids across enormous areas, even in regions nowhere near the actual blast zones, an effect the United States actually demonstrated unintentionally back in 1962 when a high-altitude test over the Pacific called Starfish Prime knocked out streetlights and set off burglar alarms in Hawaii, roughly 900 miles away from the detonation point. Follow-on strikes would almost certainly target command and control centers and remaining launch sites in an effort to prevent further retaliation. Land-based intercontinental ballistic missiles take roughly 30 minutes from launch to reach their targets on the other side of the planet, which is the entire window governments would have to detect, verify, and respond to an incoming attack. Any warhead that actually makes it through air defenses would detonate with a fireball, reaching temperatures nearly as hot as the surface of the sun, followed by a blast wave capable of vaporizing anything caught directly in its path. Survivors in areas just outside the direct blast radius wouldn't necessarily be safe either, facing firestorms and dangerously high levels of radioactivity in the hours and days that follow. But the most frightening consequences of a large-scale nuclear exchange might not even be the explosions themselves. Scientific modeling on the aftermath of a major nuclear war has consistently pointed to a phenomenon known as nuclear winter, a concept that first entered mainstream public awareness back in 1983, when astronomer Carl Sagan and a team of researchers published a landmark study, often referred to by the acronym TDPS, warning that a large-scale nuclear exchange could trigger catastrophic global cooling on a scale never before modeled. All the black carbon smoke generated by the detonations and the massive firestorms they ignite would rise into the stratosphere, where high-altitude jet streams would carry it across the entire globe, blocking out sunlight on a planetary scale. Some studies estimate this effect could cool the planet's surface temperature by as much as 40 degrees Fahrenheit, or roughly 20 degrees Celsius, a change severe enough to collapse growing seasons and agriculture across huge swaths of the world for years afterward. More recent modeling from climate scientists in the 2010s and 2020s, using far more sophisticated atmospheric models than Sagan's original team had access to, has largely reinforced those original conclusions, suggesting that even a comparatively limited regional nuclear exchange, involving just a fraction of the world's total arsenal, could still inject enough soot into the atmosphere to disrupt global agriculture and trigger famine conditions affecting billions of people who live nowhere near any of the actual blast zones. For anyone who survives the initial blasts and the fallout that follows, the greater long-term threat may end up being mass starvation rather than radiation itself. Given all of that, it's worth asking the more existential question directly. Could a full-scale nuclear war actually destroy the planet outright, in the sense of physically breaking it apart? The answer, reassuringly, is no, not even close, and comparing nuclear weapons to genuinely planet-scale natural events puts that into sharp perspective. Even Tsar Bomba, the most powerful weapon ever detonated by humans, is dwarfed by events Earth has already survived. The 1883 eruption of Krakatoa released an estimated 200 megatons of energy, roughly 4 times the yield of Tsar Bomba, hurling about 5 cubic miles of shattered rock into the atmosphere and casting an ash cloud that reached nearly 50 miles into the sky, high enough to briefly lower global temperatures by close to a full degree Fahrenheit for an entire year afterward. And even Krakatoa looks small next to the largest explosion this planet has ever experienced, the Chicxulub impact event, when an asteroid roughly 10 to 15 kilometers wide slammed into the Yucatan Peninsula in Mexico approximately 66 million years ago, traveling at nearly 45,000 miles per hour and carving out a crater 93 miles across. Estimates place the kinetic energy released by that impact at around 72 teratons, the equivalent of 72 million megatons of TNT. Even if every single nuclear warhead currently sitting in every arsenal on Earth were somehow gathered into a single pile and detonated simultaneously, the resulting explosion still wouldn't come close to matching what Chicxulub did on its own, roughly equivalent to 2 million Tsar Bombas going off at once. And despite nearly wiping out life on the planet at the time, Earth kept spinning and life came roaring back. As for the idea of nuclear weapons being used against something like the moon, the math simply doesn't work in humanity's favor there either. The moon is roughly a quarter the diameter of Earth at about 2,159 miles across, and every nuclear warhead currently in existence, fired at it simultaneously, would barely register, the equivalent of throwing a handful of pebbles at a mountain. So if nuclear weapons, even at their most powerful, can't actually destroy the planet or the moon, is there anything that theoretically could bring about a true planet-wide end to human life? There is a weapon, at least in concept, that comes disturbingly close, and it's never actually been built and deployed, at least not that's been publicly confirmed. It's called a cobalt bomb, and its horror doesn't come from explosive power at all. What it lacks in raw destructive yield, it makes up for entirely in radioactivity. Sometimes referred to as a salted or dirty bomb, a cobalt weapon is designed to blanket an enormous radius and extraordinarily persistent radioactive fallout, meaning that even people who survive the initial blast and shockwave would face a much deadlier, longer-lasting threat afterward. The concept was first described publicly by physicist Leo Szilard back in 1950, though notably, he wasn't proposing that such a device actually be built. He was warning that nuclear technology had already advanced to the point where a true doomsday weapon, one capable of ending human life on Earth entirely, was theoretically achievable. The mechanism behind it inverts the exact same physics used to make Tsar Bomba comparatively cleaner. Remember how Soviet engineers used a lead tamper around Tsar Bomba's final stage, specifically to reduce fallout? A cobalt bomb would do the precise opposite, wrapping a thermonuclear weapon in a tamper made of ordinary cobalt instead. When the bomb detonates, the intense burst of neutrons from the explosion converts that cobalt into cobalt-60, an extremely radioactive isotope, which is then vaporized in the blast itself. That vaporized cobalt would condense back out of the atmosphere and fall to Earth along with the dust and debris, contaminating essentially everything it touches across a vastly wider area than a conventional weapon of similar size ever could. And, unlike many other forms of nuclear fallout, cobalt-60 doesn't decay quickly. It has a half-life of 5.227 years, meaning it would remain dangerously radioactive for many years, even decades, after detonation, long enough that hiding in a fallout shelter wouldn't guarantee survival once you eventually had to come back out. Some scientists have speculated that only the hardiest forms of life on Earth, organisms like tardigrades, might realistically survive prolonged, widespread cobalt-6 decontamination, and even that's far from certain. Had Tsar Bomba itself been built with a cobalt tamper instead of a lead one, in its full multi-stage configuration, it would have spread a catastrophic amount of radioactive fallout across a far wider area than what actually occurred in 1961, with consequences for global health and the environment that are difficult to even fully calculate. It's a genuinely unsettling thought experiment, precisely because, unlike so much of the science fiction imagery associated with nuclear weapons, a cobalt bomb isn't science fiction at all. The physics behind it are well understood and have been for more than 70 years. The only reason such a weapon has never been built, as far as the public record shows, is that no nation has ever seen strategic value in a device whose sole purpose would be maximizing long-term radioactive contamination rather than achieving any specific military objective, and the same logic that made Tsar Bomba strategically pointless, its lack of practical deployability, applies even more forcefully to a weapon deliberately designed to poison the planet rather than defeat a target. That's a thin thread of reassurance to hang on to, admittedly, but it's also a reminder of just how much of the nuclear age has actually come down to restraint rather than raw capability. Humanity built the tools to end itself decades ago. What's kept that from happening isn't a lack of destructive power, it's the choice made and remade by leaders on every side not to use it. Whether that restraint holds, especially at a moment when testing moratoriums are being reconsidered, new missile systems are entering service on multiple continents, and the doomsday clock sits closer to midnight than it has ever been recorded, is a question nobody can answer with certainty. What we do know is that the physics hasn't changed since 1961. The stakes have simply gotten harder to ignore. Let us know what you think happens from here. Whether you think humanity manages to keep pulling back from the edge the way it always has before, or whether you think the current moment is different. And if you found this breakdown useful, stay tuned, because there's a lot more to unpack the deeper you go into this subject. And we'll keep covering it as things continue to develop. Thanks for watching.